Long before the Atlantic Ocean existed, the land beneath Florida belonged to a completely different world. It was part of Africa, buried under the swamps, limestone, and warm, shallow seas of the modern state, is a memory far older than the Atlantic Ocean, a time when the continents were fused together, when the map of Earth was almost unrecognizable, and when the ground that would one day become Florida was locked inside a vast ancient supercontinent. The evidence is written deep underground. Granite beneath central Florida matches rock found along the coast of Senegal. Ancient formations beneath South Florida share the same geological fingerprint as parts of Guinea. Fossils recovered from deep boreholes belong to marine communities found in West Africa, but nowhere else in North America. Somewhere along the way, a piece of Africa became part of America. How that happened is one of the strangest journeys in Earth's history, and even more remarkable is the fact that the rocks beneath Florida still preserve every chapter of it. So tonight we are traveling back 650 million years to the age when Florida was still part of Africa. Every landscape carries a history, although that history rarely stays where it began. To understand why the ground beneath Florida tells a story that starts on another continent, it helps to picture the surface of Earth in a different way. Imagine a planet whose outer skin is divided into immense pieces, each drifting with such patience that a human lifetime cannot perceive the motion. Their progress is measured at about the pace of a fingernail growing. Yet, given enough millions of years, that modest movement reshapes oceans, mountains, and continents beyond recognition. The rocky shell surrounding the planet is broken into these great slabs, known as tectonic plates. They float upon hotter, softer material deep within Earth, where heat generated inside the planet drives slow currents that never truly come to rest. Those currents press against the plates above, guiding them in changing directions across spans of time so immense that coastlines appear fixed only because human memory is brief. The continents seem permanent, although permanence is an illusion created by our own limited perspective. When two plates converge, neither can ignore the other forever. Sometimes one edge bends downward, descending into the interior, where increasing pressure and temperatures exceeding 1000 degrees Celsius or 1832 degrees Fahrenheit gradually recycle ancient crust into molten rock. In other places, both continental masses resist sinking, forcing the crust upward into mountain ranges that may endure for hundreds of millions of years before erosion wears them away. Elsewhere, the plates separate, allowing molten material to rise and cool into fresh crust, while a widening gap slowly grows into a new ocean basin. Among the most fascinating consequences of this restless system is the creation of something geologists call a terrain. A terrain is not defined by the country or continent where it rests today. Instead, it is recognized through its identity, the minerals inside its rocks, the fossils preserved within its layers, the chemistry locked into its crystals, and even the age of those crystals can reveal an origin far removed from its present location. Over immense stretches of time, plate movement can transport such a fragment across disappearing oceans before attaching it permanently to an entirely different continent. The foundation beneath much of Florida belongs to exactly such a fragment. Geologists know it as the Suwannee Terrane, a piece of crust whose birthplace lay along the margin of West Africa before an ancient collision joined it to North America. That union happened long before the first dinosaur appeared, during an age when the arrangement of continents bore little resemblance to the familiar globe hanging in classrooms today. Although younger layers now conceal that foundation beneath thick accumulations of limestone and sediment, its original character remains preserved within the deeper rock. This interpretation does not rest upon speculation or an isolated discovery. Independent evidence gathered through paleontology, geochemistry, radiometric dating, and paleomagnetism converges upon the same conclusion, each method arriving through its own path while reinforcing the others. Within geology, the African origin of the Suwannee terrain stands as an established understanding. Outside that field, however, it remains one of Earth's least familiar stories, resting beneath one of the most recognizable places on the map. Around 650 million years ago, the ground that would someday rest beneath Florida occupied a coastline no modern map could recognize. It formed part of Gondwana, a supercontinent spreading across nearly 100 million square kilometers, which is about 38,600,000 square miles, covering close to one-fifth of Earth's surface and lying largely within the southern hemisphere. Gondwana gathered together lands that would one day become Africa, South America, Antarctica, Australia, the Indian subcontinent, and several smaller fragments whose future paths had scarcely begun. The shoreline where the Florida fragment rested overlooked an ocean unlike any familiar sea today. Bare stones stretched across the continents without forests, grasses, mosses, or flowers to soften its outlines. No insects buzzed through the air, no reptiles crossed the ground, and no birds traced circles overhead. Even vertebrate animals had yet to appear. The atmosphere contained considerably less oxygen than the modern world, while nearly every intricate ecosystem flourished beneath rolling waves instead of across the land. Those waters nurtured forms of life that belonged to an evolutionary chapter almost impossible to picture today. During the Ediacaran period, broad, soft-bodied organisms rested upon the seafloor, absorbing nutrients in ways that still challenge scientific interpretation. Some resembled leaves pressed into fine sediment, while others branched into repeating patterns unlike any living creature. They represented an early experiment in complexity, preparing the stage for one of the most significant biological transformations Earth has ever experienced. As the Cambrian period unfolded, diversity expanded with astonishing speed in geological terms. Within only a few tens of millions of years, nearly every major animal body plan familiar today emerged in some recognizable form. Hard shells, protective armor, compound eyes, grasping limbs, and specialized feeding structures appeared across marine habitats. Evolution explored possibilities with extraordinary creativity, filling shallow seas with communities whose descendants would shape every later ecosystem. Along this Gondwanan coastline, the Florida fragment remained a passive continental margin. Geological activity there unfolded with remarkable stability. Rivers carried fine sediments toward the coast, where currents spread them across broad continental shelves. Layer after layer settled onto the seafloor, gradually burying older deposits beneath fresh accumulations. Each grain preserved traces of its surroundings, recording changing sea levels, shifting climates, and the succession of marine communities with patient precision. Nothing about this particular stretch of coast suggested that it would someday become extraordinary. It blended naturally into thousands of kilometers, which is about 621 miles, of similar shoreline extending across Gondwana's western edge. Its future significance rested in details invisible to any observer alive at the time. The chemistry locked inside cooling minerals, the ages preserved within tiny zircon crystals, and the biological remains settling through seawater together formed a signature unique to this corner of the supercontinent. Among those accumulating remains were graptolites drifting through open water, trilobites crawling across the seabed, brachiopods anchored within soft sediment, conodont animals leaving behind microscopic tooth like elements, and chitinozoans floating through ancient seas. Generation after generation entered the growing layers below, leaving an archive that endured compression, burial, continental collision, and the passing of hundreds of millions of years. Far in the future, deep drilling through northern Florida would recover that archive, revealing a shoreline whose earliest home stood beside the coast of West Africa. The strongest witness to Florida's distant birthplace never spoke through granite or magnetic minerals. It lived, fed, reproduced, and settled onto an ocean floor that disappeared hundreds of millions of years ago. Tiny shells, delicate skeletons, and fragments of long vanished creatures became part of layers of sediment that endured every continental rearrangement. Those remains still preserve the identity of the sea where they formed, and that identity belongs to West Africa. Reaching this evidence requires an extraordinary journey into the ground. Deep boreholes drilled across northern Florida descend through thick blankets of limestone before finally entering much older rocks from the Paleozoic era. Some of these wells extend farther than 1.5 kilometers, which is about 0.93 miles below the modern surface. At those depths, drill cores recover narrow cylinders of rock that have remained sealed since a world existed with entirely different coastlines and oceans. Inside those cores, paleontologists found marine invertebrates from the Ordovician, Silurian, and Devonian periods, graptolites, brachiopods, trilobites, conodon animals, and other marine organisms appear in recognizable succession through the layers. Each species occupied a particular environment and lived during a particular interval of geological history. Together, they form fossil assemblages, communities whose composition reveals far more than the identity of any single organism. They preserve the character of an entire marine ecosystem that once occupied a specific ocean basin. When researchers compared these fossil communities with records collected elsewhere, an unexpected pattern emerged. The species, their order within the rock, and the ecological relationships between them matched formations along the coasts of Senegal, Sierra Leone, and Guinea with remarkable consistency. The resemblance extended beyond individual fossils. Entire biological communities appeared to mirror one another across rocks separated today by the Atlantic Ocean, as though they had once belonged to the same shoreline. Equally significant was what the drill cores failed to contain. Comparable rocks from the ancient continent of North America preserve different marine communities, reflecting evolutionary histories that unfolded apart from those recorded inside Florida's basement. During the Paleozoic era, an ocean stretched between these distant coastlines, preventing regular exchange between their marine populations. That separation allowed each region to develop its own distinctive collection of species, leaving biological signatures that remained preserved long after the ocean itself vanished. Fossils provide an unusually dependable form of geological evidence because living communities respond directly to their surroundings. Mineral chemistry can sometimes be altered through later heating or fluid movement, and magnetic signatures may require careful interpretation. Entire ecological assemblages are considerably more difficult to misread. When dozens of species repeatedly appear together in the same sequence across widely separated rock formations, they preserve the memory of a shared environment with compelling clarity. For that reason, the fossils recovered from Florida's deepest rocks carry exceptional significance. They record a marine world that flourished before jawed fish transformed ocean ecosystems, before forests spread across continents, and before animals ventured onto land. Every preserved shell and microscopic fragment strengthens the same conclusion. Florida's oldest biological archive originated within a West African sea, remaining intact through burial, continental collision, and the passage of immense spans of time. The living communities disappeared countless ages ago, yet their record continued waiting within stone until careful hands finally brought it back into daylight. Across the horizon of that distant world stretched an ocean whose surface no longer exists, whose floor has almost completely vanished, and whose name survives only through geology. The Iapetus Ocean occupied the space between the Florida fragment along the margin of Gondwana and the continent that would eventually become North America. Named after the figure from Greek mythology who was the father of Atlas, it occupied a position that, much later, would be inherited by the Atlantic itself. At its greatest extent, the Iapetus spread across hundreds of kilometers, that is nearly hundreds of miles, of open water, broad enough to isolate coastlines for immense spans of time. Marine currents circulated independently on each side, carrying nutrients, larvae, and microscopic life within separate oceanic systems. Evolution followed different paths across those waters. Species adapted to one coastline rarely reach the other, allowing entirely distinct biological communities to flourish. That long isolation explains why the fossils preserved within Florida's deepest rocks belong to a world shared with West Africa instead of ancient North America. The ocean itself rested upon crust unlike the continents bordering it. Oceanic crust formed from dense volcanic rock created where molten material cooled beneath spreading seafloors. Continental crust contained lighter rocks that floated higher upon the planet's interior. This difference governed the future of the Iapetus. Whenever oceanic crust encountered continental crust during plate convergence, the denser oceanic plate curved downward and descended into Earth's interior. There, temperatures exceeding 1,000 degrees Celsius or 1,832 degrees Fahrenheit gradually transformed solid rock into molten material that became part of the mantle once again. That process unfolded with extraordinary patience. The Iapetus did not disappear within a dramatic geological instant. Its floor descended little by little over hundreds of millions of years, consumed along subduction zones that bordered the shrinking basin. Every year, the ocean narrowed by only tiny amounts, impossible for any living creature to perceive. Yet those nearly imperceptible changes accumulated until an entire ocean approached its conclusion. Subduction also reshaped the surface above. As descending plates released water into the overlying mantle, portions of that mantle melted and generated rising magma. Volcanoes emerged along curved chains, creating island arcs scattered across the ocean. These volcanic archipelagos drifted with the moving plates and gradually encountered the eastern margin of North America. During the Ordovician and Devonian periods, repeated collisions added these fragments to the continent, enlarging its edge piece by piece while steadily reducing the distance that still separated Gondwana. Every collision altered the geography of the closing ocean. New mountain belts rose where crust compressed, while older volcanic chains became permanent additions to continental margins. None of these events ended the story by themselves. Instead, they prepared the boundary for the much greater encounter approaching from across the remaining water. Around 325 million years ago, the Iapetus had nearly vanished. Only a narrowing marine corridor remained between the advancing edge of Gondwana and eastern North America. Carried upon that approaching continental margin was the Florida fragment itself, still inseparable from the African coast where its story had begun. The sea that once divided two distant worlds had almost completed its own long disappearance, leaving only the closing distance between continents whose meeting would reshape both forever. Continents do not collide with the violence of a single moment. Their encounters unfold across intervals so immense that entire groups of organisms appear and disappear while the meeting continues. Around 325 million years ago, the final narrowing of the Iapetus Ocean brought the leading edge of Gondwana into contact with eastern North America. Geologists know this prolonged event as the Alleghanian orogeny, one of the greatest continental collisions preserved in Earth's history, and its imprint remains visible across the eastern United States today. The advancing African plate did not strike like a falling object. Instead, it pressed steadily against North America for approximately 65 million years. That span exceeds the time separating the present day from the extinction of the non-avian dinosaurs. Throughout those millions of years, unimaginable pressure accumulated as neither continent could easily descend beneath the other. Their buoyant continental crust resisted sinking, leaving compression as the only path forward. Rock that had rested nearly level for countless ages began to bend under this persistent force. Layer after layer folded into broad arches and deep troughs. Enormous fractures developed where one mass of crust rode over another, creating immense thrust faults that displaced rocks across great distances. Individual cliffs and ridges seen today represent only the weathered remnants of structures that once reached much greater heights, before erosion gradually softened their outlines. From this sustained compression rose the ancestral Appalachian Mountains. Modern forests and rounded summits reveal only the final weathered chapter of their history. During their youth, these mountains rivaled the highest ranges on Earth. Many researchers estimate that the loftiest peaks reached between 4 kilometers, which is about 2.5 miles, and 5 kilometers, which is about 3.1 miles, above the surrounding landscape. Their jagged skyline extended for thousands of kilometers, which is about 1,864 miles, forming a nearly continuous barrier along eastern North America. Conditions became especially intense within the southern Appalachians. There, horizontal shortening reached extraordinary proportions. Portions of the crust compressed by as much as 300 kilometers, which is about 186 miles, as gigantic sheets of rock advanced over one another along gently inclined fault surfaces. These displaced masses stacked together across enormous distances, thickening the crust and elevating the growing mountain chain with every stage of compression. At the front of the approaching Gondwanan margin traveled the fragment that would someday support Florida. It represented the first section of African crust to meet North America during this continental convergence. Gradually, the relentless pressure welded that fragment against the continent. The joining occurred without any possibility of reversal. Once fused, the rocks became part of a single continuous crust, even though each retained the geological memory of a very different origin. The boundary where this union occurred still exists. Geologists call it the Swanee Suture Zone, a buried scar extending beneath parts of southern Alabama and Georgia. It marks the place where African basement rock became permanently attached to North America through the accumulated force of continental collision. Nothing visible at the surface reveals its presence, yet the rocks preserve the complete record of that meeting. Long before dinosaurs, flowering plants, or mammals entered the story of Earth, the future foundation of Florida had already completed the journey that carried a fragment of West Africa onto an entirely different continent. Far from the coastline that carried the future Florida fragment, another corner of Gondwana supported one of the most formidable hunters the planet had yet produced. across the broad floodplains of what is now the Karoo Basin in South Africa. Life unfolded beneath a climate shaped by alternating wet and dry seasons. Among stands of Glossopteris trees and dense patches of horsetail plants, a predator moved with an anatomy unlike anything that had come before, occupying a place along the evolutionary path that would never appear again. The Gorgonopsid belonged to the synapsids, the branch of life that eventually produced every mammal alive today, including human beings. Even so, it cannot be called either reptile or mammal in any familiar sense. It occupied an earlier chapter, preserving characteristics of both while remaining entirely its own creation. Evolution explored many possibilities during the Permian period, and the Gorgonopsid represented one of its most successful experiments. The largest known forms, including Inostrancevia, reached about 3½ meters, which is about 11 feet 6 inches in length and weighed roughly 700 kilograms. More familiar members of the group, such as Gorgonops, were considerably smaller, carrying a body mass similar to a modern lioness at approximately 98 kilograms. Their limbs extended directly beneath the body instead of projecting outward from the sides, creating a more efficient stride that supported longer pursuit across open ground than most contemporary animals could achieve. Its skull carried the feature for which it is remembered. Saber-shaped canine teeth reached as much as 12 centimeters, which is about 4.7 inches, making them the earliest true saber teeth known in the history of life. These elongated canines evolved tens of millions of years before the first cat appeared. Accommodating them required an extraordinary jaw that could open to nearly 90 degrees, allowing the upper teeth to clear the lower jaw before closing with devastating precision. Many of the animals sharing this landscape belonged to another remarkable group, the Dicynodonts. These sturdy plant eaters ranged from pig-sized species to forms approaching the size of modern cattle. Toothless beaks clipped vegetation, while paired tusks projected from the upper jaw, giving the group its name, meaning two dog teeth. They browsed among Glossopteris forests and seasonal wetlands, gathering wherever water remained available after the rains had passed. Evidence preserved in fossil skeletons suggests that Gorgonopsids relied upon ambush more than prolonged pursuit. Powerful forelimbs probably helped restrain struggling prey while the enlarged canines delivered deep wounds. Afterward, the predator could follow the weakening animal until exhaustion brought the hunt to its conclusion. Hundreds of millions of years later, saber-toothed cats evolved a strikingly similar strategy through entirely independent evolution, illustrating how natural selection can arrive at comparable solutions across distant ages. The Karoo landscape itself experienced warm seasonal conditions averaging between 16 degrees Celsius or 61 degrees Fahrenheit and 20 degrees Celsius or 68 degrees Fahrenheit. Rivers shifted across broad floodplains, carrying sediment that buried bones after seasonal floods. Those deposits eventually hardened into the rocks that preserve this vanished ecosystem today. Although separated from the future Florida fragment by thousands of kilometers, which is about 1,864 miles, every part of this environment belonged to the same continuous supercontinent. The predator never crossed paths with the place now called Florida because that place did not yet exist. Only its foundation rested within Gondwana, sharing the same continental journey. When the Permian-Triassic extinction arrived around 252 million years ago, more than 90% of marine species and about 70% of land vertebrates disappeared. Every Gorgonopsid vanished with them, leaving only fossils to record a world that had already begun to drift toward an entirely different future. Nothing assembled by plate tectonics remains together forever. The same forces that compressed continents into a single landmass eventually begin pulling them apart again, turning former lines of collision into places of separation. Around 200 million years ago, Pangaea entered that next chapter. The supercontinent that had united nearly all major landmasses started to fracture, beginning a transformation that would ultimately produce the familiar arrangement of continents seen today. The earliest stage of this breakup appeared as a network of deep cracks spreading through the continental crust. One particularly important system developed where Africa, North America, and South America met. Here, heat rising from Earth's interior weakened the overlying crust until it stretched beyond its limits. Molten rock ascended through these fractures, feeding repeated volcanic eruptions while gradually forcing the land apart. What began as narrow rift valleys slowly expanded into elongated basins bordered by faulted cliffs and newly formed volcanic landscapes. These developing fractures did not spread randomly across the continent. They tended to exploit older weaknesses already preserved within the crust. Many originated along ancient collision zones where rocks had once been compressed, folded, and welded together during the assembly of Pangaea. Those scars remained mechanically different from the surrounding crust, making them favorable pathways for renewed tectonic movement millions of years later. As separation accelerated between Africa and North America, the growing rift approached the region where the Florida fragment had become attached during the Alleghanian orogeny. The original collision had created the Swanee suture zone, yet the new tear did not trace that boundary with perfect precision. Instead, the developing rift shifted slightly from the earlier scar, carving a different route through the continental crust. That subtle change determined the future of an entire geological fragment. Had the fracture followed another course, the Florida fragment might have remained attached to Africa as the continents separated. Instead, the new plate boundary formed east of the fragment. When the crust finally divided into independent plates, Florida remained connected to North America while Africa continued drifting away across the widening gap. A geological homeland, established hundreds of millions of years earlier, disappeared beyond an ocean that had only begun to exist. The newborn Atlantic looked nothing like the immense ocean familiar today. At first, it consisted of a narrow marine passage bordered by active volcanoes and fresh basaltic crust forming along its center. Heat from rising magma kept the surrounding crust elevated, while repeated eruptions built new seafloor between the separating continents. With every passing million years, additional molten rock solidified within the expanding basin, pushing Africa and North America steadily farther apart. Deep within southern Florida, basement rocks preserve evidence of this remarkable transition. Volcanic minerals, formed during the rifting event, contain distinctive isotopic signatures that record the conditions under which they crystallized. Those chemical fingerprints remain embedded within the rock, allowing geologists to identify the interval when continental separation reshaped the region forever. They provide another independent record, confirming the sequence already revealed through fossils, structural geology, and ancient crustal relationships. When the Atlantic continued widening through the ages that followed, the decision had already been made. Africa traveled eastward, carrying much of Gondwana with it. The Florida fragment remained fixed upon the North American plate, although its deeper identity still reflected the coast where its history had first begun. The ocean between them grew broader year after year, while the geological memory of their shared origin remained preserved within the rocks themselves. Imagine four investigators arriving independently at the same destination, each following a different trail, and using different tools. None relies on the work of the others, yet every path converges upon the same conclusion. That is how geologists came to understand the hidden origin of Florida's deepest foundation. The case was never built from a single remarkable discovery. It emerged gradually as separate branches of Earth science uncovered evidence that aligned with striking precision, creating a geological reconstruction that has become firmly established. The first line of evidence comes from paleontology, the study of ancient life. Deep boreholes drilled through Florida's younger limestone eventually reached rocks that formed hundreds of millions of years before dinosaurs appeared. Preserved within those rocks were marine fossils belonging to organisms that inhabited long vanished seas. Graptolites, brachiopods, trilobites, conodonts, and other invertebrates appeared together in combinations that closely matched fossil communities preserved along the western margin of Africa. The sequence of species, their ecological associations, and their positions within successive rock layers all corresponded with formations found in regions that are now Senegal, Guinea, and neighboring parts of West Africa. Comparable rocks from North America contained different biological communities, reflecting development within another ocean basin. Chemistry provided an entirely separate path toward the same destination. Minerals retain the elemental proportions present when they formed, creating distinctive chemical identities that often survive for immense spans of time. Granite buried between 1.7 kilometers, which is about 1.1 miles, and 2.4 kilometers, which is about 1.5 miles, beneath Osceola County, closely matches the composition of the Koya granite in Senegal. Rhyolitic volcanic rocks, recovered from Florida boreholes, also display chemical relationships with formations along the western African margin. Farther south, the St. Lucie metamorphic complex shares characteristics with rocks belonging to the Roclide mountain belt of Guinea. These similarities are too detailed and systematic to represent coincidence. A third line of investigation depends upon zircon crystals, tiny mineral grains that preserve remarkable records of geological time. When zircon forms, it incorporates radioactive elements that decay at predictable rates over immense intervals. Measuring those decay products allows scientists to determine the crystal's age with extraordinary precision. Zircons, recovered from Florida's buried basement, repeatedly yield age distributions characteristic of West African continental crust. Those same age patterns are absent from comparable basement rocks elsewhere in North America. Each crystal functions like a durable timestamp carried across geological history, preserving evidence of where its parent rocks first originated. The fourth line of evidence comes from paleomagnetism. As molten rock cools, magnetic minerals align themselves with Earth's magnetic field. Once the rock solidifies, that orientation becomes locked within the mineral structure, preserving the latitude where crystallization occurred. Basement rocks beneath Florida record magnetic directions consistent with formation in Gondwana rather than within the ancient position of North America. Although continents wander across the globe, these magnetic signatures remain preserved, allowing scientists to reconstruct former continental positions with remarkable confidence. Each discipline stands on its own methods, measurements, and standards of evidence. Fossils reveal biological relationships. Chemistry identifies shared origins of rocks. Zircon dating establishes geological ancestry through time. Paleomagnetism reconstructs former continental positions. None depends upon the others for its conclusion, yet everyone points toward the same history. Together they reveal that Florida's buried foundation originated along the western margin of Gondwana, traveled into North America during continental collision and remained there when Africa drifted away. That remarkable agreement across independent fields transforms an intriguing possibility into one of the clearest forensic reconstructions in modern geology. Some borders are marked by rivers, mountain ranges, or coastlines. Others exist entirely beyond ordinary sight, preserved within layers of rock that reveal themselves only through careful measurement. Beneath southern Alabama and Georgia lies one such boundary, concealed beneath younger sediments and crossed every day without notice. Geologists know it as the Suwannee Suture Zone, one of the most important geological boundaries in North America because it preserves the place where two continents became one. A suture forms when continental plates collide and the crust becomes permanently joined. Unlike an active fault, where movement continues along a fracture, a suture records the final sealing of an ancient collision. The Suwannee Suture Zone reaches as much as 100 kilometers in width, which is about 62 miles, forming a broad transition where crust that originated along Gondwana meets the older rocks of Laurentia, the continental core of North America. Although hidden beneath thick blankets of sediment, the boundary remains preserved in the chemistry, structure, and physical properties of the rocks below. Crossing from one side of the suture to the other is equivalent to stepping between geological histories that developed in separate parts of the world for hundreds of millions of years. North of the boundary, basement rocks belong to the North American craton, a stable continental foundation that had already existed for well over 1 billion years before the collision occurred. South of the boundary, the buried basement tells another story. There, the rocks carry chemical characteristics, mineral compositions, and geological histories that correspond with the western margin of Gondwana, linking them to what is now West Africa. Nothing visible at the surface announces this transition. Forests, farms, neighborhoods, and highways extend uninterrupted across the region. The evidence emerges through geophysical surveys, capable of detecting contrasts buried far below. Among the most significant is the Brunswick magnetic anomaly, a broad magnetic signature extending across southern Georgia and Alabama. Igneous and metamorphic rocks contain minerals that respond differently to Earth's magnetic field according to their composition and geological history. Mapping those variations reveals a continuous pattern that closely follows the position of the ancient continental junction, providing scientists with an invaluable guide to the buried collision zone. The Brunswick magnetic anomaly has become one of the most extensively studied geophysical features in eastern North American geology because it consistently aligns with evidence gathered from drilling, rock chemistry, structural mapping, and radiometric dating. Each method approaches the problem from a different direction, yet all reinforce the same interpretation. The magnetic boundary is not an isolated curiosity. It represents another expression of the collision that permanently attached the Florida fragment to North America during the formation of Pangaea. Even after the continents fused together, the crust retained the memory of that immense compression. Sutures often remain mechanically weaker than surrounding rock, making them more responsive when later tectonic forces reshape a continent. During the breakup of Pangaea and the opening of the Atlantic Ocean, stresses once again concentrated around this inherited seam. Although the new rift ultimately formed elsewhere, the ancient junction still responded to changing forces within the crust, demonstrating that structures created hundreds of millions of years earlier could continue influencing Earth's evolution long afterward. The Suwannee Suture Zone, therefore, represents far more than a buried geological curiosity. It is the preserved contact where African crust ends and North American crust begins, an invisible boundary separating two profoundly different continental histories. Hidden beneath younger landscapes, it remains the enduring scar of a collision that reshaped a supercontinent and permanently determined the geological identity of Florida. There was a span in Florida's story when nothing resembling modern Florida existed. After continents had collided, mountains had risen, and the Atlantic Ocean began its gradual birth, the African fragment that had become attached to North America entered a far less dramatic chapter. It slipped below sea level and remained there for roughly 100 million years. During that immense interval, no forests covered it, no rivers crossed it, and no land animals wandered above it. Warm tropical seas stretched across its surface while time accumulated grain by grain. This prolonged flooding resulted from a process known as thermal subsidence. As the newly formed Atlantic Ocean widened, the crust bordering its passive continental margin gradually cooled. Hot rock occupies more space than cool rock, so as the underlying lithosphere lost heat, it contracted and became denser. That increase in density caused the edge of the continent to sink. The Florida platform descended with it, settling beneath shallow seawater through a movement measured in millimeters across many human lifetimes, yet continuing without interruption for millions of years. The waters covering the platform differed greatly from the dark depths commonly associated with the open ocean. Sunlight reached the seafloor across broad expanses, nourishing algae, corals, shell-forming organisms, and countless microscopic creatures. The environment resembled the modern Bahama Banks, where clear tropical seas extend across wide carbonate platforms. With little sediment arriving from distant mountains, the water remained exceptionally transparent, allowing marine life that produced calcium carbonate skeletons to flourish across enormous areas. Generation after generation, those organisms lived, reproduced, and died. Their shells, skeletons, and tiny protective coverings drifted downward until they settled across the platform. Layer slowly settled upon layer. Pressure from newly deposited material gradually compressed older deposits into limestone. The accumulation advanced at a pace almost beyond ordinary imagination, often measured in mere millimeters over 1,000 years. Individual lifetimes vanished without leaving visible change, yet the combined work of countless organisms transformed the submerged platform into one of the thickest carbonate successions on Earth. Across 100 million years, which is about 62 million miles. No, correction, not miles. Across 100 million years, this steady accumulation produced limestone reaching nearly 5 kilometers in thickness, which is about 3.1 miles in parts of the Florida platform. Every layer preserved evidence of changing marine communities, shifting sea levels, and evolving climates. Tiny fossils, chemical traces, and subtle variations in sediment became pages within an immense geological archive. What appeared from above as a tranquil, tropical sea was continuously writing an extraordinarily detailed history beneath its surface. Far below those accumulating limestones, the older African basement remained remarkably unchanged. The crystalline rocks that had once formed part of Gondwana carried the signatures acquired hundreds of millions of years earlier during volcanic activity, continental assembly, and collision. Thick carbonate deposits acted as a protective blanket, shielding the basement from erosion and limiting chemical alteration. While oceans expanded, continents drifted, and new ecosystems emerged overhead, the deeper foundation preserved its inherited identity with remarkable fidelity. This contrast between surface transformation and buried stability explains why the evidence discussed earlier survived into the present. Reef builders, shell producing organisms, and tropical seas completely altered the appearance of the platform, yet they never erased the deeper record of continental origin. Instead, they concealed it beneath an immense archive of younger rock. The African fragment endured beneath those limestones exactly where tectonic forces had left it, wading through another 100 million years of Earth's history before erosion, drilling, and careful scientific investigation would finally reveal the remarkable journey hidden below Florida's familiar landscape. Life transformed the submerged Florida platform into one of the richest tropical seas of the Cretaceous world. Sunlight poured through clear water, feeding immense communities that stretched across broad carbonate shelves. Beneath the surface, generation after generation of marine organisms built thriving ecosystems that endured for tens of millions of years. Few traces remained visible from above, yet every shell, reef, and drifting skeleton added another page to the long history accumulating over the buried African foundation. Among the most remarkable inhabitants were the rudists, unusual relatives of modern clams that bore little resemblance to familiar shellfish. Some species reached nearly 1 meter in length, which is about 3 feet. One shell commonly anchored itself upright within the seafloor, while the other formed a lid, creating a structure unlike almost any living bivalve. Crowded together in extraordinary numbers, these animals constructed enormous carbonate reefs along the margins of the Florida platform. Coral existed alongside them, yet rudists became the dominant reef builders throughout many tropical seas, shaping coastlines through their own distinctive architecture for millions of years before vanishing forever during the end Cretaceous Paleogene extinction. Those expanding reef systems altered the surrounding environment as effectively as any mountain range influences weather on land. Their growing barriers restricted the exchange of seawater between the platform interior and the open ocean. Inside this sheltered region, evaporation frequently exceeded the arrival of fresh seawater. Salinity steadily increased, encouraging dissolved minerals to crystallize onto the seafloor. Thick deposits of evaporite minerals accumulated beneath the lagoon, preserving evidence of conditions that changed gradually across immense spans of time. These mineral layers remain buried within Florida's subsurface, recording the chemistry of seas that disappeared long before the first human ancestor appeared. Swimming through these waters were ammonites, elegant cephalopods whose coiled shells contained a series of internal chambers that regulated buoyancy. Their lineage had survived repeated global upheavals across more than 300 million years. Countless forms drifted, hunted, and reproduced above the platform during the closing portion of their remarkable history. Fossils recovered from deep Florida wells preserve their delicate shells alongside remains of rudists, revealing that these ancient communities flourished together across the same shallow marine landscape. Farther from the reefs, larger predators ruled the open water. Mosasaurs, reaching lengths of about 17 meters, which is about 56 feet, propelled themselves with powerful tails through the warm sea. Their flexible jaws captured fish, ammonites, and nearly any creature unfortunate enough to cross their path. Along deeper platform margins, plesiosaurs traveled with broad flippers, their elongated necks allowing careful strikes at passing prey. Above the water, enormous pterosaurs crossed coastal skies, their shadows moving across lagoons and reef crests before disappearing beyond the horizon. Every organism in this flourishing ecosystem lived without any awareness of the foundation supporting its world. Beneath several kilometers of accumulating limestone, the transported fragment of Gondwana remained preserved, with its original geological character intact. Marine life continuously reshaped the surface, yet none of those transformations disturbed the older rocks resting far below. Seas changed, reef builders rose and vanished, predators appeared and disappeared, and sediments continued their patient descent. Through every chapter, the concealed basement retained the memory of a distant shoreline once joined to West Africa, carrying that forgotten origin beneath one of the greatest marine environments of the age of dinosaurs. A different cast of life entered the waters above the Florida platform after the catastrophe that ended the age of non-avian dinosaurs. Around 66 million years ago, the impact that triggered the Cretaceous Paleogene extinction swept away the ammonites, the rudist reefs, and countless other marine lineages that had flourished for ages. As ecosystems recovered, the sea did not return to its former state. New creatures filled the empty niches, and among them were animals whose bodies recorded one of evolution's most remarkable transformations. The Eocene epoch, extending from about 55 million years ago until 34 million years ago, unfolded during one of the warmest intervals of the past 65 million years. Average global temperature stood roughly 8 degrees Celsius to 10 degrees Celsius higher than those of the modern world, or about 46 degrees Fahrenheit to 50 degrees Fahrenheit warmer. Tropical forests spread into regions that today experience long winters, while warm currents flowing through the Tethys Sea carried heat across much of the planet. The shallow sea covering the Florida platform shimmered beneath those currents, supporting a rich web of marine life over limestone that continued to accumulate grain by grain. Among the most extraordinary inhabitants were the archaeocetes, early whales that had only recently returned to the ocean after descending from mammals that once walked entirely on land. Their skeletons preserved a fascinating mixture of old and new anatomy. Some retained small but functional hind limbs, too reduced for walking yet still complete enough to reveal their terrestrial ancestry. Others had progressed farther along the evolutionary path, their rear limbs diminished to tiny remnants hidden within the body. Across successive generations, the sea became a place where natural selection refined swimming, breathing, hearing, and movement until the familiar whale form gradually emerged. One ruler stood above nearly every other predator. Basilosaurus reached lengths approaching 18 meters, which is about 59 feet, its elongated body gliding through warm coastal waters with remarkable efficiency. Despite its name suggesting a reptile, Basilosaurus was fully a whale, equipped with powerful jaws lined by sharp teeth capable of seizing fish, sharks, and smaller marine mammals. Fossils preserved within Florida limestone confirm that these predators hunted across waters covering much of what is now the southeastern portion of the United States, leaving evidence of encounters that unfolded over seas long vanished. Near sheltered shallows, another lineage explored a different future. Primitive sea cows browsed on marine vegetation growing across the platform. Some early species still possessed sturdy limbs, ending in small hooves, reflecting their relatively recent departure from life on land. Their movement through coastal lagoons contrasted with the swift pursuit of Basilosaurus, yet both belonged to mammalian branches, adapting in separate ways to the same marine environment. Around them swam broad rays, numerous sharks, sea turtles, and crocodilians suited to saltwater habitats, each contributing to an ecosystem unlike the one that had disappeared only a few million years earlier. Every creature crossing this Eocene sea lived above a foundation whose history reached far beyond its own lineage. Thousands of meters of limestone, that is nearly 16,404 feet, now separated thriving marine communities from the transported rocks resting below. The buried fragment from Gondwana remained unchanged as whales perfected life in the ocean overhead, preserving within its crystalline depths the memory of a distant African coast, while entirely new chapters of Earth's living story unfolded above it. Separation can endure even after continents have found their places. While the buried fragment beneath Florida rested securely against North America, the landscape above told a different story for tens of millions of years. Water occupied the space between them, forming a broad marine passage known as the Georgia Trough. Across that interval, the Florida platform remained detached from the mainland, surrounded by warm seas that shaped its future with remarkable patience. The Georgia Trough extended across what is now southern Georgia, linking the Gulf of Mexico with the Atlantic Ocean through an open marine corridor. Far from being a narrow channel, it persisted as a substantial seaway whose circulation influenced the movement of water across the southeastern margin of the continent. Ocean currents flowing through this passage redirected materials that otherwise would have spread southward, creating conditions unlike those developing only a comparatively short distance away. Those diverted materials came from the gradual erosion of the Appalachian Mountains. Rivers carried sand, silt, and clay toward the coast, producing what geologists call siliciclastic sediment. Such sediment transforms shallow marine environments by clouding the water and covering the organisms responsible for building limestone. Reef communities flourish where sunlight penetrates easily and suspended particles remain scarce. The currents within the Georgia Trough repeatedly swept much of this sediment away from the Florida platform, preserving the exceptional clarity needed for uninterrupted carbonate production. As a result, marine organisms continued constructing layer upon layer of limestone while sediments from the mountains accumulated farther north. Shells, microscopic plankton, algae, and countless other creatures contributed calcium carbonate to the seafloor, each generation adding another thin page to an expanding geological archive. The contrast between the two neighboring regions became increasingly pronounced. North of the seaway, siliciclastic deposits thickened. South of it, carbonate rocks continued growing with remarkable consistency across the platform. Planetary change gradually altered that balance. Antarctica drifted away from South America, allowing the opening of the Drake Passage. Once this marine gateway became established, a powerful current began circulating around Antarctica without interruption from continental barriers. The newly formed Antarctic Circumpolar Current isolated the southern continent, encouraging the expansion of long-lasting ice sheets. Global temperatures declined through the Oligocene epoch, sea level slowly fell, and changing coastlines modified the pathways followed by marine currents. Sediment transported from the Appalachian region gained greater opportunity to accumulate within the Georgia Trough, reducing its depth across immense spans of time. The transformation unfolded through countless generations, measured more effectively in geological layers than in ordinary calendars. Little by little, the seaway became shallower as sediment continued filling the remaining basin. Marine circulation weakened, coastlines shifted, and the long-standing barrier separating the Florida platform from the continental mainland approached its conclusion. Around 23 million years ago, the connection finally emerged as deposition and falling sea level completed the closure of the trough. For the first time since the widening Atlantic had reshaped this corner of the planet, uninterrupted land stretched between Florida and the rest of North America. The platform that had spent millions of years developing in relative isolation now shared a continuous terrestrial pathway with the continent to its north. Beneath the surface, the transported rocks from Gondwana remained unchanged, while above them a new chapter began, shaped by migration, changing ecosystems, and landscapes that had at last become physically joined after an interval almost beyond ordinary imagination. Far below neighborhoods, forests, springs, and coastlines lies a monument assembled grain by grain across an almost unimaginable span of time. The rock supporting modern Florida is more than a foundation. It is the compressed memory of countless vanished seas, built from the remains of organisms that drifted, swam, settled, and disappeared over roughly 150 million years. Every layer preserves another interval in a story written without interruption above the transported fragment of Africa. Limestone owes its existence to living creatures. In warm, shallow seawater, dissolved calcium carbonate became the material from which shells, skeletons, and protective coverings were built. Tiny drifting plankton, reef builders, mollusks, echinoderms, algae, and many other forms of marine life borrowed those dissolved minerals throughout their lives. After death, their remains settled across the seafloor in an almost continuous fall. Burial gradually increased as newer generations accumulated above older ones. Pressure compacted these deposits, while mineral rich water passed through the sediments, binding loose particles together until soft layers became solid limestone. The pace of that construction remained almost beyond ordinary perception. A layer measuring only a few millimeters could represent thousands of years of biological activity. Century after century blended into thicker deposits. While sea level shifted, climates fluctuated, and entire ecosystems appeared before yielding to successors. In some regions beneath Florida, the accumulated limestone eventually reached nearly 5 kilometers in thickness, that is nearly 3,107 miles. Each interval became a geological page whose fossils and chemistry preserve evidence of changing oceans across 150 million years of continuous deposition. Reading downward through this immense sequence resembles turning the pages of an archive arranged by time instead of ink. Deeper Cretaceous layers preserve rudist reef communities together with ammonites that vanished during the Great Extinction at the close of that era. Younger Paleocene and Eocene deposits contain early whales still bearing traces of their terrestrial ancestry, accompanied by primitive sea cows exploring warm coastal waters. Higher Oligocene rocks preserve shark teeth, dugong relatives, mollusks, and countless smaller organisms. Every transition records another transformation in marine life, while the African basement remained sealed far below, untouched by the changing worlds above. Although limestone appears durable, it continues changing after its formation. Rainwater absorbs carbon dioxide from the atmosphere and additional carbon dioxide released by soils rich in plant life. This produces a mild natural acid capable of dissolving calcium carbonate little by little. Water descending through fractures enlarges tiny openings into passages, chambers, and underground drainage networks. The process advances with extraordinary patience, sometimes requiring many thousands of years before noticeable cavities emerge within the rock beneath the landscape. Eventually, the ground above these expanding spaces can no longer support its own weight. Sediment collapses into the void, and the surface drops with little warning. Roads, fields, buildings, ponds, and parking areas may suddenly become part of the underground landscape. One widely documented collapse even claimed a bedroom while its occupant slept, illustrating the continuing influence of processes that began when these limestones first accumulated beneath warm prehistoric seas. The landscape above may appear stable across a human lifetime, Yet the stone below continues responding to water exactly as it has for millions of years. Beneath every familiar horizon rests an immense cemetery of marine life, transformed into rock, preserving vanished oceans while gradually reshaping the land that now depends upon it. The first footsteps across Florida did not belong to reptiles or dinosaurs. They belonged to mammals entering a landscape that had only recently emerged from a sea lasting tens of millions of years. After the Georgia Trough finally closed during the Miocene, a continuous land bridge united the Florida platform with the North American mainland. The long marine chapter had ended, and a procession of unfamiliar travelers began crossing onto ground that had never before supported large terrestrial life. Their arrival is preserved with remarkable clarity at the Thomas Farm Fossil Site in northern Florida, one of the most important Miocene fossil localities in eastern North America. Its sediments contain an extraordinary gathering of species that spread across the newly connected peninsula. Three-toed horses grazed open woodland and grassy clearings. Several rhinoceros species wandered alongside tapirs browsing among dense vegetation. Giant ground sloths moved deliberately through the landscape, while bear dogs patrolled as formidable predators. Elephant relatives, known as gomphotheres, added further variety to an ecosystem assembled from migrants reaching a place that had previously existed only beneath shallow tropical seas. The timing of this transformation appears almost perfectly recorded in the fossil archive. No confirmed land mammal fossils older than the Miocene have been discovered in Florida. Marine organisms dominate the older limestone, reflecting the platform's prolonged history beneath warm water. Then, following the establishment of a permanent land connection, terrestrial mammals appear in abundance. The sequence resembles a doorway opening in stone, with the geological record preserving the moment when migration became possible across a route that had not existed for millions of years. Those pioneering animals encountered a landscape unlike the modern peninsula. Thick forests and extensive wetlands had not yet developed across much of the region. Broad limestone plains stretched beneath relatively thin, sandy soils, while groundwater circulated through dissolving carbonate rock to form springs that discharged clear fresh water across the surface. Rivers followed youthful drainage systems, and low relief dominated the horizon. The terrain reflected its recent emergence from the sea, retaining many characteristics inherited from its long underwater past. As the peninsula continued evolving, sediments and organic remains accumulated across central Florida, eventually creating the deposits now known from the Bone Valley region. This area became one of the richest fossil repositories from the Miocene and Pliocene in the world. Phosphate-rich sediments preserved shark teeth washed inland from nearby seas, dugong ribs from coastal waters, horse teeth from grazing mammals, mastodon molars, turtle shells, fish bones, and countless smaller remains. Together they formed a layered record showing marine and terrestrial life becoming intertwined as shorelines advanced and retreated across the changing peninsula. Each skeleton added another page to a story, extending far deeper than the animals themselves. Every rhinoceros track crossed limestone built from marine organisms that had lived through vanished oceans. Every grazing horse walked above reefs compressed into stone over 150 million years. Beneath those limestones rested the transported basement carried from the western margin of Africa during the assembly of the supercontinent hundreds of millions of years earlier. None of the mammals roaming this newly connected land could perceive that inheritance. They crossed an ordinary landscape shaped by springs, forests, and open plains, while far below their feet remained a fragment of another continent, preserved through collisions, drifting oceans, and immense spans of geological time. Across the broad plains of Pliocene Florida, movement filled nearly every horizon. Herds grazed across open grasslands, predators followed well-worn game trails, and rivers linked freshwater springs to coastal estuaries. Between roughly 5 million and 2.6 million years ago, the peninsula supported one of the richest assemblies of large animals anywhere on Earth, a landscape whose diversity rivaled the modern Serengeti while unfolding atop a foundation shaped by a far older geological journey. The mammal community reached an extraordinary scale. Several species of saber-toothed cats occupied different hunting roles within the same ecosystem. Giant ground sloths stretched to 5 meters in length, which is about 16 feet, and weighed several tons as they browsed leaves from shrubs and low trees. At least 6 horse species grazed side by side, each adapted to slightly different food sources. Mastodons wandered through wooded patches, while gomphotheres, close relatives of elephants, crossed the floodplains with distinctive, elongated jaws. Tapirs browsed near waterways, peccaries rooted through dense vegetation. Giant armadillos searched for food beneath the soil. Spectacled bears ranged across mixed habitats, and camels moved through open country that looked remarkably different from the modern peninsula. Life extended beyond the shoreline with equal abundance. Warm coastal waters supported dugongs feeding on seagrass meadows, porpoises traveling in social groups, several whale species, broad-winged rays gliding over sandy bottoms, and immense sharks ruling the food chain. Among them swam Carcharocles megalodon, the largest shark presently known from Earth's history. Its teeth, some measuring more than 18 centimeters, which is about 7 feet, would be incorrect. Instead, some exceeded 18 centimeters, which is about 7 inches, preserving evidence of an animal whose body length may have approached 18 meters, which is about 59 feet. Those remarkable teeth continue to emerge from Florida rivers and beaches after millions of years, carried upward as younger sediments gradually erode away. Another transformation unfolded when the Isthmus of Panama rose high enough to connect North America and South America around 3 million years ago. That new corridor launched the Great American Biotic Interchange, allowing animals from 2 continents to expand into unfamiliar territory. Florida became one of the meeting grounds for this exchange. Giant terror birds entered from the south. Glyptodonts the size of compact automobiles lumbered into new habitats, and South American relatives of horses and tapirs joined species already established across the peninsula. The result was a biological mosaic assembled through migration, adaptation, and competition over countless generations. Every migration followed paths across limestone, formed from marine life that had accumulated through 150 million years of deposition. Freshwater springs emerged after filtering through those carbonate rocks, nourishing grasslands and wetlands that sustained remarkable communities of mammals and birds. Deep below that limestone remained the transported crust from the western edge of Africa, unchanged despite the passage of oceans, extinctions, and continental rearrangements. The creatures roaming this flourishing peninsula knew only the landscapes before them, while the oldest chapter of the ground supporting every footstep rested far below, preserved through geological time until the modern world inherited both its wildlife and its remarkable foundation. The outline of Florida has never remained fixed for long. Coastlines that seem permanent on modern maps have advanced and withdrawn many times, responding to rhythms set far beyond the peninsula itself. During the Pleistocene, beginning about 2.6 million years ago, repeated cycles of glaciation and warming reshaped the platform more profoundly than any chapter since its long separation from the mainland had finally ended. Each great advance of continental ice locked immense volumes of seawater onto the land. At the height of the coldest intervals, the Laurentide ice sheet covered much of northern North America, drawing enough water from the oceans that global sea level dropped by as much as 120 meters, which is about 394 feet. Florida, built upon a broad and gently sloping platform, responded dramatically. During the most recent glacial maximum, around 20,000 years ago, the peninsula stretched far beyond its modern shoreline, reaching nearly twice its present width as newly exposed land emerged from the retreating sea. Those newly uncovered plains extended westward into what is now the Gulf of Mexico and eastward beneath the modern Atlantic Ocean. Broad limestone surfaces lay beneath thin sandy soils, interrupted by freshwater springs, scattered wetlands, scrub forests, and open savannas. Rivers crossed ground that has since disappeared beneath coastal waters. Herds of woolly mammoths wandered beside mastodons, giant ground sloths browsed through scattered woodlands, dire wolves pursued migrating prey, American lions stalked large herbivores, and Florida's spectacled bears occupied habitats that no longer exist. Every migration unfolded across terrain created by fluctuating seas, while the transported African basement remained far below, unchanged through each climatic cycle. Evidence for this enlarged landscape survives in places where dry ground has long vanished. Fossil hunters and commercial dredging operations working offshore have recovered mastodon teeth, mammoth molars, giant ground sloth bones, horse teeth, and many other remains from the floor of the Gulf of Mexico. These discoveries rest at depths reaching well beyond 100 meters, which is about 328 feet, confirming that areas now covered by seawater once supported thriving ecosystems. The submerged fossil record preserves an earlier coastline with remarkable clarity, revealing valleys, stream channels, and grazing lands now concealed beneath marine sediments. The return of warmer conditions unfolded through many stages instead of a single uninterrupted rise. As continental ice melted, water flowed back into the oceans and shorelines advanced inland. Some intervals brought comparatively gradual flooding, while others produced more rapid marine transgressions that transformed coastal plains within relatively short spans of geological time. Habitats shifted repeatedly as rivers adjusted their courses, springs found new outlets, and expanding estuaries replaced grasslands that had endured throughout colder climates. Modern Florida represents only one position within this continuing cycle. Earlier ages placed the shoreline many kilometers beyond its present margin, while much older intervals submerged nearly the entire platform beneath tropical seas. Future changes will continue to redraw those boundaries as climate influences the balance between ice and ocean. Across every transformation, the limestone accumulated through countless marine generations has supported changing landscapes above it. While the African crust, resting beneath that immense carbonate foundation, has witnessed alternating worlds of land and sea without surrendering the record of its distant origin. A different rhythm settled across Florida as the last great ice age loosened its hold on the planet. The broad grasslands that had supported immense grazing herds gradually contracted, waterways shifted across the landscape, and forests spread into places that had once remained open. Within this changing world, one of the most remarkable animal communities in North America disappeared over a span that, in geological terms, lasted only a moment. By roughly 10,000 years ago, mammoths, mastodons, Giant ground sloths, saber-toothed cats, dire wolves, native horses, and gomphithers had vanished from the peninsula. The reason remains one of paleontology's most enduring debates because more than one force may have shaped the outcome. Rising global temperatures at the close of the Pleistocene altered rainfall patterns, vegetation, and the distribution of fresh water. Expansive savannas gradually gave way to denser woodlands that favored different kinds of animals. Large grazers lost much of the habitat that had sustained them for countless generations. At nearly the same time, human communities reached Florida, carrying finely crafted stone tools into landscapes occupied by animals that had never before encountered this particular kind of hunter. Whether climate, hunting pressure, or a combination of both proved decisive, continues to be examined through new discoveries. Florida preserves exceptional evidence because many of its natural features became remarkable vaults for ancient remains. Sinkholes, spring vents, and river channels collected bones that escaped destruction after death. Mineral-rich water protected skeletons with unusual completeness, allowing scientists to reconstruct vanished ecosystems in remarkable detail. Excavations within the Peace River and the Osceola River have yielded mastodons, giant ground sloths, horses, and many other species, some preserved with bones still lying in their original anatomical positions. A few discoveries also display cut marks matching stone tools, linking people directly with animals living during the closing stages of the Ice Age. Among the most extraordinary locations is Little Salt Spring in Sarasota County. Today, the site lies underwater within a deep sinkhole, accessible only through careful diving expeditions. Long before rising seas and groundwater filled the chamber, it served as part of the surrounding landscape. Researchers recovered the remains of a giant land tortoise that appears to have been prepared by humans around 12,000 years ago. That discovery represents some of the earliest convincing evidence for human activity in Florida, preserving a brief encounter between newly arrived people and creatures approaching the end of their long history. The world that emerged afterward differed profoundly from the one those early inhabitants inherited. European explorers arriving during the 16th century encountered subtropical forests, wetlands, rivers, and coastlines occupied by deer, black bears, alligators, and countless smaller species. The immense mammals that had shaped the peninsula for hundreds of thousands of years had already faded into memory. Hydrological systems continued evolving, vegetation settled into new patterns, and surviving wildlife adapted to conditions established after the extinction. Throughout every biological transformation, the deeper foundation remained unchanged. Limestone accumulated through long vanished seas continued supporting springs, rivers, and forests, while the transported crust from Western Africa rested far below the surface, preserving a story written hundreds of millions of years before the final mammoth crossed the peninsula. When the Great Ice Age fauna disappeared, the last major biological chapter above that buried foundation came to a close, leaving the landscape that would eventually become familiar as Florida. Far below forests, rivers, and growing cities, another landscape continues its patient journey through stone. It cannot be seen from the surface, yet it reaches across nearly the entire peninsula, filling ancient passages carved through limestone that began its existence beneath warm seas more than 100 million years ago. This is the Floridan aquifer system, among the most productive freshwater reservoirs on Earth, supplying drinking water to millions of people while preserving the physical memory of a vanished marine world. Its existence depends entirely upon the character of limestone. Unlike dense crystalline rock, Limestone contains countless openings created during its long history. Tiny spaces remained between grains. Fractures widened under pressure, and circulating groundwater dissolved channels through layers built from shells and skeletons. The result resembles a sponge on an immense geological scale, although every pore and passage formed from compressed marine organisms that settled upon the Florida platform through nearly 150 million years of uninterrupted deposition. Rainwater filters downward into this network and begins a gradual passage through stone that has been evolving since the age of dinosaurs. The aquifer extends beneath roughly 100,000 square miles, which is about 259,000 square kilometers, covering all of Florida and reaching into parts of Georgia, Alabama, and South Carolina. Water does not remain motionless within this system. Seasonal rainfall enters through permeable ground, sinks into the limestone, and moves under natural pressure through interconnected conduits. Some pathways require years to complete their journey, while others continue for decades before returning to daylight through springs, rivers, or coastal discharge zones. Every movement follows passages shaped by dissolution over immense spans of time. Where pressure carries groundwater back to the surface, Florida's famous springs emerge with remarkable consistency. Wakulla Spring, Silver Springs, Itchituckney Springs, and many others release clear water throughout the year at about 20 degrees Celsius or 68 degrees Fahrenheit. Deep burial within kilometers of limestone shields the water from seasonal extremes before it reaches the surface. That steady temperature creates environments that change very little from one season to the next, even when conditions above ground fluctuate with passing weather. Such stability has supported communities of living creatures for thousands of years. West Indian manatees gather within these spring systems during winter because the flowing water never approaches freezing temperatures. Fish, freshwater turtles, crustaceans, and delicate invertebrates complete their life cycles within habitats shaped by constant flow and dependable warmth. The springs become enduring refuges where ecological relationships persist with unusual continuity, sustained by water that has completed an exceptionally long underground voyage. Each leader emerging from these springs has crossed limestone composed of organisms that flourished in vanished oceans. Dissolved calcium carried within the water originated from shells built by rudists, foraminifera, mollusks, and countless microscopic marine creatures whose remains accumulated layer upon layer across the prehistoric seafloor. Their bodies became stone, the stone became an aquifer, and the aquifer now returns fresh water to the surface. Every spring, therefore, carries a faint chemical inheritance from oceans that disappeared long before the first primates began their own story. The evidence did not arrive as a dramatic revelation. It accumulated with the patience of the rocks themselves, one drilled core after another, one puzzling measurement beside the next. For many years, geologists studying the deepest layers beneath Florida held fragments of a story that refused to fit the accepted picture. Each new sample seemed to whisper that something about the peninsula's foundation belonged somewhere else, although no accepted explanation yet existed to unite those scattered clues. During the early and middle decades of the 20th century, companies searching for petroleum and fresh water drilled progressively deeper wells across Florida. Cylinders of granite, metamorphic rock, and fossil-bearing sediment reached laboratories where specialists cataloged every detail. Certain fossil communities differed from expectations. Mineral compositions resembled formations known from distant regions instead of nearby North America. Chemical signatures preserved within ancient crystals also resisted easy interpretation. Reports carefully documented these anomalies, then placed them into archives because no established geological model could explain why such unexpected material rested beneath Florida's younger limestone cover. The turning point arrived through a transformation in the way scientists understood the planet itself. During the 1960s, the theory of plate tectonics gained widespread acceptance, replacing older ideas of fixed continents with a world whose crust moved upon shifting plates. Within this new framework, geologists recognized that fragments of continental crust could travel enormous distances before becoming attached to another continent. The concept of a displaced crustal block, called a terrane, suddenly provided language capable of explaining observations that had remained unresolved for decades. Once that framework existed, older discoveries acquired entirely different meaning. Zircon crystals preserved within Florida's basement rocks carried isotopic ages, matching formations from Western Africa. Studies using samarium and neodymium isotope systematics strengthened the comparison. Detailed geochemical analyses revealed striking similarities between Florida granite and rocks exposed across parts of present-day West Africa. Airborne magnetic surveys traced the buried Suwannee suture, identifying the ancient boundary where the displaced crust became welded to North America during continental collision hundreds of millions of years earlier. Independent investigations approached the mystery from different directions, yet each conclusion reinforced the others. This progression illustrates an enduring pattern within scientific discovery. Observations often appear before the ideas capable of explaining them. Instruments collect measurements faithfully, regardless of whether anyone understands their significance. Samples, recovered during the 1940s and 1950s, preserved reliable evidence from the beginning, although their broader meaning remained concealed until plate tectonics reshaped geological thought. The theory did not replace the data. Instead, it revealed relationships that had always existed within the measurements themselves. Today, the African origin of Florida's buried basement belongs to established geology, supported by decades of converging evidence rather than a single, decisive experiment. Visitors arrive from every corner of the world, crossing beaches, forests, wetlands, and cities without realizing that the oldest rocks beneath their feet began their journey beside a different continent. The landscape above has changed beyond recognition through passing ages, yet the concealed foundation preserves a record of that distant beginning, waiting beneath layers of limestone for anyone willing to read the language written in stone. The story does not end at the edge of the Florida Peninsula. The buried fragment that traveled across an ancient ocean extends beyond modern coastlines and state borders, continuing beneath landscapes that appear entirely ordinary from the surface. What first seemed like an isolated geological curiosity gradually revealed itself as part of a much broader foundation, one that reaches beneath portions of the American Deep South with remarkable continuity. Geologists identify this buried crustal block as the Suwannee terrane. It stretches northward beneath southern Georgia and into parts of Alabama before disappearing beneath younger layers of sediment. Although Florida forms its most familiar expression, the terrane itself is considerably larger than the peninsula resting above it today. Deep drilling, seismic surveys, and geochemical analyses have shown that these concealed rocks share a common history, preserving characteristics that distinguish them from the older North American continental interior lying farther inland. At basement level, portions of Georgia and Alabama therefore belong to the same displaced fragment that underlies Florida. The forests, rivers, farms, and towns above reveal nothing of this inheritance, yet far below the surface, the crystalline rocks record a distant origin connected with the assembly and later breakup of Gondwana. Their long journey ended hundreds of millions of years ago when continental collision joined them permanently to eastern North America, after which younger sediments gradually concealed every visible trace of that dramatic arrival. Florida is also part of a larger geological mosaic that characterizes much of the eastern margin of the continent. Farther north, the Carolina terrane preserves a different origin story. Current evidence suggests that much of this terrain developed as volcanic islands and related crustal fragments near the margins of Gondwana before successive mountain building events carried them against ancestral North America. Those collisions occurred during separate chapters of continental assembly, producing landscapes that eventually became integrated into a single expanding landmass while preserving distinctive histories within their deepest rocks. Viewed from the surface, the eastern United States appears continuous, its mountains, valleys, and coastal plains blending into one another across great distances. Viewed from basement level, the picture changes completely. Stable North American crust occupies the interior, while the eastern margin consists of numerous terranes, each representing crust formed in different environments and transported through plate motion before becoming attached. Ancient sutures separate these fragments, marking vanished oceans whose existence survives only through careful geological investigation. A traveler driving from Miami through Georgia, across the Carolinas, and onward toward New England would unknowingly pass above a succession of foundations assembled across roughly 400 million years. Some originated beside Gondwana, others formed within volcanic island arcs or along distant continental margins. Additional fragments preserve pieces of oceanic crust caught between colliding continents before those oceans disappeared entirely. Modern highways ignore boundaries that remain unmistakable within the rocks themselves. Florida therefore represents one chapter within a much larger continental narrative. Its African basement is among the clearest examples of long-distance crustal transport preserved beneath the eastern United States, although it is accompanied by many neighboring fragments with equally remarkable histories. Together, they demonstrate that continents are not permanent monoliths. They are enduring assemblies, constructed piece by piece through collisions so gradual that only the patient record, preserved within stone, reveals how many distant homes contributed to the landscape that exists today. Far from the beaches and springs of Florida, the worn ridges of the Appalachian Mountains rise in long folds across the eastern landscape. Their weathered slopes seem to belong to a different story, separated by forests, rivers, and more than 1,000 kilometers, which is about 621 miles. Deep within Earth's crust, however, both landscapes preserve the consequences of the very same continental collision recorded in different forms but born during the same chapter of planetary history. Between roughly 325 million and 260 million years ago, Africa and ancestral North America converged as the supercontinent of Pangaea assembled. The immense compressional forces of the Alleghanian mountain building event folded, faulted, and uplifted enormous volumes of crust, creating a mountain chain that many geologists believe rivaled the modern Himalayas in elevation. At the same time, the Suwannee terrane, carrying the basement that now underlies Florida, became permanently attached to the southern edge of North America along a deep crustal boundary that remains detectable through modern geophysical studies. Although separated by great distance today, these geological features remain linked through their common origin. The Appalachian Mountains preserve the visible scars of compression, while Florida preserves a buried fragment that journeyed across an ancient ocean before becoming part of the same continent. One feature rises above the horizon, the other rests far below younger sedimentary layers. Together, they preserve complementary evidence of a single tectonic event that reshaped eastern North America. The connection continued long after the collision itself had ended. Newly formed mountains began to wear away under rainfall, rivers, and weathering. For millions upon millions of years, vast quantities of sand, mud, and gravel flowed southward into nearby basins. Among those receiving this steady supply was the Georgia Trough, whose gradual infilling transformed a broad marine passage into shallower environments where carbonate sediments and incoming continental deposits accumulated together. That prolonged process eventually helped establish the conditions allowing Florida's platform to connect with the mainland, opening pathways that later supported expanding terrestrial ecosystems. Even today, erosion has not entirely ceased. Streams draining the Appalachian region continue transporting sediment toward the Atlantic coastal plain and the Gulf Coast, although the volumes are greatly reduced compared with those carried from the towering mountains of the distant past. Modern Florida is shaped primarily by carbonate deposition, coastal processes, groundwater movement, and changing sea levels, yet fine sediment derived from the continent still contributes to the evolving surface. Every grain represents another small step in a cycle that has continued since those mountains first began to wear down. Seen together, the Appalachian Mountains and Florida reveal two enduring expressions of one ancient collision. One tells its story through folded ridges and exposed metamorphic rocks. The other conceals its history beneath limestone deposited across many millions of years, where African crust remains locked below younger layers that transformed into the peninsula known today. Their relationship demonstrates that geological events rarely produce a single outcome. A continent grows through many connected consequences, each unfolding across immense spans of time, leaving evidence scattered across landscapes that appear unrelated until the deeper history written within the rocks brings them together. A map gives every continent a clear outline, bordered by coastlines that appear fixed and permanent. From that familiar view, the world seems settled into orderly shapes that have always existed. Geology offers a different perspective. It replaces certainty with motion, revealing that continents are not enduring objects, but evolving collections of crust, assembled through repeated episodes of collision, separation, erosion, and renewal across spans of time that far exceed biological memory. The history preserved beneath Florida illustrates this idea with unusual clarity. The basement rock supporting the peninsula has occupied many identities without changing its physical substance. It formed along the margin of what is now West Africa, became part of the Gondwanan supercontinent, approached ancestral North America as tectonic plates converged, and was permanently joined during continental collision. Later, as Pangaea fragmented, that same crust remained attached to North America, while new ocean basins opened nearby. Marine sediments accumulated above it for many millions of years before the limestone platform eventually emerged as dry land. Every stage lasted longer than the entire history of humanity. Viewed in this way, a continent is not defined by political borders or familiar coastlines. It is a mosaic assembled from fragments with different origins, each preserving its own earlier journey. Some pieces formed within stable continental interiors, others arrived as volcanic island chains, slices of oceanic crust, or continental fragments carried across vanished oceans. Their boundaries remain detectable through changes in mineral composition, isotopic signatures, magnetic properties, and structures deep within the crust, even after mountains have eroded and younger rocks have concealed the original collisions. The buried Suwannee suture records one of those ancient unions. Extending beneath parts of Georgia and Alabama, it marks the boundary where crust derived from Gondwana became welded to ancestral North America during the assembly of Pangaea. The ocean that once separated those regions disappeared hundreds of millions of years ago, consumed by subduction and continental convergence. Its waters are gone. Its seafloor has vanished into Earth's interior. Yet the scar left by that closure remains preserved within the crust. Forests, rivers, towns, and generations of life have come and gone above it without revealing the boundary lying far below. Deep time also changes the meaning of place itself. A location is often imagined as something permanent, carrying the same identity through every age. Geological history reveals continuous transformation instead. Coastlines migrate, mountains rise and wear away. Seas advance across continents before retreating again. Plates shift by thousands of kilometers, carrying familiar landscapes into entirely different positions on the globe. Each setting inherits traces of earlier worlds while preparing the foundation for those yet to come. From the perspective of human history, calling Florida part of North America is entirely correct. From the perspective of Earth's longer narrative, the deeper basement remembers a far older chapter written beside the margin of another continent. Neither description cancels the other. They belong to different scales of time, each accurate within its own frame of reference. Continents are therefore less like permanent monuments and more like living archives, assembled piece by piece, preserving every collision, separation, and reunion within the rocks that continue supporting the world above them. Across eastern Africa, the landscape itself reveals that continents are still changing. Long valleys stretch toward the horizon, bordered by uplifted escarpments and scattered volcanoes whose presence marks a crust under tension. This is the East African Rift System, one of the clearest places on Earth where the earliest stages of continental separation can be observed. It offers a living glimpse of processes that once shaped the foundation beneath Florida, although the outcome remains far in the future and many chapters have yet to unfold. The rift extends for about 3,000 kilometers, which is about 1,864 miles, from the Afar region through Ethiopia and farther south across Kenya, Tanzania, Malawi, and Mozambique. Here, the African continent is gradually stretching apart as tectonic forces thin the crust along zones of inherited weakness. Measurements made with satellites show that the opposing sides are moving apart by only a few millimeters each year, a pace almost impossible to notice within a human lifetime, yet capable of transforming continents over many millions of years. As the crust stretches, it becomes thinner and begins to subside. Magma rises through fractures from deeper within Earth's mantle, feeding volcanoes and creating new igneous rock. Some valleys continue sinking, while nearby blocks are lifted higher, producing the dramatic relief that characterizes the region today. Lakes such as Tanganyika, Malawi, and Albert occupy many of these deep depressions, collecting water where the land has gradually lowered. Together, they illustrate an intermediate stage in continental breakup, comparable to conditions that preceded the opening of the Atlantic Ocean many millions of years ago. If extension continues for tens of millions of years, seawater could eventually invade the developing basin, forming a narrow sea connected to the surrounding ocean. Continued spreading would then generate new oceanic crust between the separating land masses, gradually widening the gap into an ocean basin. Geological evidence strongly supports this general sequence because it has occurred repeatedly throughout Earth's history. The exact timing, however, remains uncertain, and future tectonic changes could alter the pace or geometry of the process before complete separation takes place. Should a continental fragment eventually separate from Eastern Africa, its journey would only be beginning. Carried by moving tectonic plates, it could drift across an ocean for many millions of years before approaching another continent. There, convergence might close the intervening ocean basin, bringing the wandering fragment into collision with unfamiliar crust. The rocks would preserve minerals, fossils, and chemical signatures inherited from their original homeland, even after becoming welded into an entirely different continental margin. Future geologists, living perhaps 100 million years from now, might encounter that buried fragment through deep drilling or geophysical investigation. At first, its composition could appear inconsistent with surrounding rocks, just as unusual basement samples once puzzled researchers studying Florida. Careful comparison of mineral ages, isotopic compositions, structural patterns, and regional geology could eventually reveal that the fragment originated somewhere far away, preserving evidence of an earlier geography erased from the surface. The story recorded beneath Florida is therefore neither unique nor finished. It represents one completed example within an ongoing planetary cycle in which continents assemble, divide, migrate, and reunite across immense intervals of time. Eastern Africa demonstrates that the same fundamental forces remain active today, continuing the patient rearrangement of Earth's surface, one movement at a time, far beyond the span of any single generation. A familiar shoreline can hold more history than any monument. White sand reflects the morning light. Waves erase footprints almost as soon as they appear, and the landscape offers little hint that its foundation has traveled farther than almost any place on the continent. The sensation arrives only after the layers are imagined together, each resting upon another, extending downward through intervals of time that stretch beyond ordinary comprehension. The sand itself carries the first chapter of that descent. Much of it ultimately traces its origin to minerals weathered from the Appalachian Mountains, whose rocks were lifted during the continental collision that permanently attached the Swanee terrain to North America. Rivers transported countless grains southward across immense spans of time, wearing them smaller with every journey. They settled along coastlines, supported by limestone, that formed beneath warm seas, creating beaches whose beauty is tied to events separated by hundreds of millions of years, yet joined through continuous geological change. Looking deeper reveals another succession. Near the surface lie comparatively young limestones deposited within the past few million years. Farther below rest layers from the Eocene epoch, formed when early whales still retained echoes of their terrestrial ancestry while swimming through tropical seas above the platform. Beneath those are Cretaceous limestones, accumulated from reefs built by rudist bivalves and countless microscopic marine organisms. Those sediments settled upon crust that had already completed its voyage from the margin of ancient Africa, carrying minerals whose internal structure preserved memories of environments far older than the peninsula itself. The basement rock remains concealed beneath this enormous stack of younger deposits, inaccessible except through deep drilling and geophysical investigation. Within its crystals, magnetic minerals became aligned with Earth's magnetic field at the moment they cooled from molten rock. Those microscopic orientations have survived later burial, continental collision, and the opening of oceans, allowing geologists to compare them with rocks preserved across the Atlantic. Together with mineral ages, chemical compositions, and structural relationships, they form an enduring record of a shared origin that surface scenery never reveals. Water creates another connection between the present landscape and its remote foundation. Rain sinks into fractured limestone, moving through passages enlarged over millions of years before emerging from springs. The water usually reaches the surface at about 20 degrees Celsius or 68 degrees Fahrenheit because it has remained insulated from seasonal weather while circulating underground. Along its route, it dissolves calcium from shells deposited during the Cretaceous period, carrying tiny traces of organisms that flourished long before mammals became the dominant land animals. Even the sinkholes scattered across the peninsula belong to this same history. They develop as groundwater gradually enlarges cavities within soluble limestone until the overlying material can no longer support its own weight. Roads, forests, and neighborhoods occupy the surface above these changing spaces, often without any visible sign of the slow transformation below. The process unfolds over years, centuries, or longer, reminding us that landscapes continue evolving even when daily life suggests permanence. Seen together, the beach, the spring, the sinkhole, and the water drawn from a household well become parts of one uninterrupted narrative. Each exists because continents collided, oceans opened and closed, reefs flourished and vanished, and a fragment of African crust found a lasting place beneath southeastern North America. Ordinary moments unfold above that inheritance every day, while the deeper story remains patiently written in stone below our feet. Identity is often imagined as something fixed, rooted to a single place from beginning to end. The deeper record beneath Florida suggests another possibility. Its oldest foundation has occupied different positions on the globe, crossed vanished oceans, endured continental collisions, disappeared beneath younger rock, and emerged into scientific understanding only after an extraordinary span of time. The journey belongs to the crust itself, even though the stone has never possessed any awareness of the path it followed. The basement rock did not decide to separate from the margin of ancient Africa. It did not anticipate the closing of an ocean or the force that joined it to North America during the formation of the supercontinent Pangaea. It did not notice the later rifting that opened the Atlantic Ocean and left it permanently attached to the western continent, while Africa drifted away once more. Layer after layer accumulated above it, eventually creating the limestone platform, springs, beaches, and forests that define the modern landscape. Throughout each transformation, the rock remained exactly what physical processes allowed it to become, preserving evidence without intention. That enduring evidence gives geology one of its greatest strengths. Minerals retain chemical compositions inherited from their original source. Tiny zircon crystals preserve ages that survive repeated cycles of mountain building and erosion. Magnetic minerals remember the orientation of Earth's magnetic field when molten rock cooled into solid stone. Even after hundreds of millions of years, these details remain available for careful measurement. The record is not written in words, yet it can still be read by those who understand its language. Every discovery about Florida's deepest foundation emerged from that remarkable persistence. Geologists compared ages, mineral chemistry, isotopic compositions, structural patterns, and fossil evidence gathered from many places separated by the Atlantic Ocean. No single observation carried the entire story. Each added another sentence until a coherent narrative appeared. Beneath the peninsula rested a fragment whose history matched rocks preserved in Western Africa far more closely than those forming the interior of North America. The journey had never been erased. It had only been concealed beneath younger chapters. Nature offers many examples of continuity through transformation. Rivers alter their channels while still carrying water toward the sea. Mountains gradually wear away, although their sediments continue traveling across continents. Coral reefs become limestone after burial, and limestone later dissolves into passages that guide groundwater toward springs. Each stage differs from the last, yet every stage preserves traces of what came before. Change and continuity exist together, woven into the same process across immense intervals of time. Florida therefore illustrates an idea extending beyond maps and coastlines, places more dynamic than everyday experience suggests. A landscape may occupy one location while preserving the memory of another within its deepest structure. Continents themselves become collections assembled from pieces with separate beginnings, joined through collisions that reshape the planet again and again. Their present arrangement reflects only one moment within an ongoing sequence. Standing upon the peninsula today means standing above a foundation that has crossed oceans, survived continental assembly and separation, and carried its earliest signature across almost unimaginable expanses of time. Nothing visible at the surface reveals that inheritance directly. Yet every carefully examined crystal, every matching chemical pattern, and every buried contact between ancient rocks affirms the same enduring truth. Origins may become deeply covered, but they remain present, waiting with remarkable patience until the earth itself offers the means to read their story. The map hanging on a classroom wall appears complete, its coastlines settled into familiar positions that seem destined to remain unchanged. Deep time offers another perspective. Every continent occupies a temporary arrangement, part of an ongoing pattern of separation, movement, collision, and renewal that has repeated throughout Earth's history and continues beneath the oceans at this very moment. The same forces that gathered Gondwana, assembled Pangaea, and ultimately carried the Suwannee terrain into southeastern North America have never ceased. Heat escaping from Earth's interior drives slow circulation within the mantle. That movement influences the rigid plates above, guiding them across the planet at speeds comparable to the growth of human fingernails. Oceans widen where new crust forms, while elsewhere, older seafloor descends back into the mantle along subduction zones. Across tens and hundreds of millions of years, these modest motions reshape the entire face of the world. Because plate motion follows recognizable physical principles, geologists have developed several plausible visions of Earth's distant future. One possibility is called amassia, in which the Pacific Ocean gradually contracts until North America and Asia meet near the Arctic. Another is Novopangaea, where the Atlantic Ocean continues expanding while the Pacific closes, producing a different arrangement of continents. A third model, known as Pangaea Proxima, suggests that changing plate boundaries could eventually reverse the widening Atlantic, allowing the continents to reunite in a configuration reminiscent of the former supercontinent. Each proposal differs in detail, yet all describe a planet that remains dynamic rather than fixed. Within every scenario, continental fragments continue their individual journeys. Some margins will experience renewed mountain building as collisions compress thick sequences of sediment into towering ranges. Other regions may split apart as fresh rifts develop, eventually admitting seawater and creating new ocean basins. Pieces of continental crust may become isolated during these events, drifting independently before joining distant landmasses many millions of years later. Future geologists, examining rocks formed during those distant ages, may discover familiar clues preserved within unfamiliar surroundings, just as the African signature beneath Florida was recognized long after its voyage had ended. The Suwannee terrain will also remain part of this unfolding process. Buried beneath thick accumulations of limestone and younger sediments, it travels with the North American plate wherever that plate ultimately moves. Its minerals, chemical characteristics, and inherited structures will accompany every future collision. Even if new mountain ranges someday rise above it, or fresh sediments conceal it more deeply, the evidence of its earliest origin will remain locked within the rock itself, awaiting methods of investigation that have not yet been imagined. Nothing in this sequence unfolds according to intention or destination. Plate tectonics follows physical laws operating over intervals almost impossible to visualize within a human lifetime. Continents assemble, separate, migrate, and reunite because energy continues flowing outward from Earth's interior, sustaining cycles that began soon after the young planet cooled enough for stable crust to form. Every familiar coastline, therefore, represents only a passing arrangement within an immensely longer narrative. The forgotten interval when Florida occupied the edge of ancient Africa belongs to that greater continuity. It was neither an isolated curiosity nor an exception to Earth's history. It stands as one completed passage in an enduring cycle that continues beneath today's oceans, carrying every continent, every mountain, and every buried fragment toward landscapes that exist only in the distant future of the planet. Memory is usually imagined as something carried by living minds, fading with time until only fragments remain. Geology reveals another form of memory, one that exists without thought or intention. A crystal, a fossil, or a buried layer of stone preserves moments from worlds that disappeared long before any creature capable of remembering had evolved. Florida's basement offers one of the clearest demonstrations that rock can retain an astonishingly complete record across spans of time, almost beyond imagination. The story began when the rocks of the Suwannee terrain crystallized along the margin of what is now West Africa. Minerals cooling from molten material aligned themselves with the magnetic field that surrounded the young crust. Isotopes became fixed within growing crystals, preserving chemical relationships established at the instant of formation. Marine sediments settled across nearby seafloors, enclosing shells and microscopic organisms whose forms reflected the ecosystems of that distant coastline. Each process left a different kind of signature. None depended upon the future existence of continents, oceans, or even the survival of the landscapes where those rocks first formed. Immense geological change followed. Oceans opened and later disappeared. Continental collisions folded mountain belts across thousands of kilometers, which is about 621 miles. Rifting separated crust that had once been joined, sending fragments toward unfamiliar destinations. Thick layers of younger sediment accumulated above the buried basement until limestone covered it beneath several kilometers, which is about 2 miles, of rock. Those additions concealed the older foundation without rewriting the evidence locked inside it. The deepest layers remained insulated from erosion, preserving information that would have been far more vulnerable had they remained exposed at the surface. When drilling projects eventually reached those concealed rocks, the recovered cores appeared ordinary at first glance. They were narrow cylinders, only a few centimeters in diameter, carrying markings that seemed meaningful only to trained specialists. Within those samples rested mineral grains, fossil assemblages, and chemical compositions that refused to match expectations for the surrounding North American crust. Each observation contributed another piece to a pattern. As analytical techniques improved through later decades, the separate clues aligned into a coherent history, pointing unmistakably toward an African origin preserved beneath the Florida platform. That realization carries a meaning extending beyond one peninsula. Geological history survives because every major event leaves physical traces governed by natural laws rather than memory or tradition. Magnetic minerals retain the direction of fields that vanished long ago. Isotopic systems preserve chemical relationships established during crystallization. Fossils record communities that flourished before later oceans arrived and retreated. Even when continents separate, reunite, and drift apart again, those records endure within the material itself, waiting until methods become precise enough to read them accurately. Florida's buried foundation, therefore, stands as more than an unusual geological curiosity. It demonstrates that Earth rarely destroys the evidence of its own past. More often, the planet folds that evidence into newer layers, shelters it beneath younger landscapes, and carries it forward through changing ages. The record remains available for those willing to descend far enough, recover the right samples, and interpret them with patience. The rock remembers without effort, preserving a coastline that vanished hundreds of millions of years ago, while the world above it continues changing from one age to the next. Every landscape offers a story at its surface, yet some of the longest chapters lie far beyond ordinary reach. Florida appears to be a place of beaches, wetlands, springs, forests, and broad limestone plains. Beneath those familiar scenes rests another history, one concealed so deeply that generations passed without knowing it existed. The forgotten age endured far longer than the rise of forests on land, longer than the reign of the dinosaurs, and longer than every extinction and recovery that reshaped the living world. Even so, almost none of it can be recognized by looking across the ground today. Its absence from everyday experience does not reflect a lack of evidence. The record survives because it lies protected beneath younger layers. Reaching it demands drilling more than 1 kilometer, which is about 0.62 miles, through limestone and sediment before the buried basement finally appears. Above that foundation rests the aquifer, followed by younger rock shaped by changing seas, and finally the landscape familiar to every visitor. Each layer belongs to a different chapter, preserving the one below instead of replacing it. The deepest rocks remain shielded from weathering, carrying a history that endured because it stayed beyond ordinary contact with the surface. Even the features that seem most characteristic of Florida hint at that concealed foundation. Sinkholes develop as groundwater dissolves limestone over immense spans of time, gradually enlarging underground chambers until the roof can no longer support the weight above. When collapse finally comes, the opening reveals another step downward through the accumulated record. The event does not expose the African basement itself, yet it reminds us that the visible landscape forms only the uppermost portion of a much deeper structure assembled across hundreds of millions of years. Florida's celebrated springs provide another connection with that layered past. Rainwater enters porous limestone, travels through networks of fractures and cavities, and eventually returns to daylight after passing through rocks formed from the remains of countless marine organisms. During that journey, the water acquires the chemical character of the formations surrounding it, emerging clear and remarkably consistent in composition. Far below those circulating waters, the buried continental foundation continues, supporting every younger layer above it, carrying a geological identity established long before the Atlantic Ocean existed. Within that foundation rests the Osceola granite, concealed beneath Osceola County and preserved beneath extensive younger deposits. Its chemistry, mineral composition, and isotopic character closely match granites of West Africa, providing one of the strongest pieces of evidence that this part of Florida originated along the Gondwanan margin before continental rearrangement carried it away. The rock remains more than 1 kilometer, which is about 0.62 miles beneath the surface, unchanged by the shifting landscapes that accumulated overhead through later ages. The forgotten age, therefore, has never truly vanished. It survives beneath every shoreline, every river, every spring, and every forest, waiting without urgency beneath layers deposited by changing seas and passing eras. Geological time asks for nothing except patience. The continents continue their gradual motion, landscapes continue to evolve, and the buried record remains complete, preserving the memory of a coastline that once belonged to another world. Florida stands upon that inheritance today, its deepest foundation still carrying the unmistakable signature of an African beginning, waiting for each new generation willing to look far enough below the surface to read the story written there.